All right, so good. So I'm supposed to have a changer somewhere, but it's small enough for me to go back and forth. All right, so what we are going to be doing is we're going to be starting off with, I mean, Alice one. So the so it goes like this. This is the second book, and this is through the Looking Glass. So what happens is Alice is running and running really fast. It's the land of the Red Queen. And after a while, she stops and she sees that she is at the same point where she was, after running all this while. And she turns to the Red Queen and said, "What is happening? What sort of a world is this?" And this is the answer of the Red Queen. So here it takes all the running you can do to stay in the same place. If you wish to run, I mean, if you wish to get somewhere, you need to run twice as fast. So with inspiration from this, we're going to do something very strange. We are going to take the speed of light out to zero. So this is going to be, you are, of course, familiar with non-relativistic systems where speed of light goes to infinity, light flows open out, but there's this other weird apparently crazy, where the speed of light goes to zero, the light goes close up. And these theories are called Carrollian theories. And I think so it was named after Louis Carroll by London in the 1960s. And so this, apparently, a very strange thing. Why should you at all speak about something like this? If you tell the man on the street, well, you shouldn't do that. But if you tell most people, that you're looking at something where speed of light has gone to zero, they'll be like, go away. But this interesting thing is that it has a lot of really interesting applications, which are, we are actually being able to see this. As we go along, we will. This doesn't seem to work. On off.
And just to ask, Arjun,
Yeah.
In terms of dimension-less parameters, when you do mechanics, we say it's velocity over speed.
Yes.
And here
it is the same basis. Yeah.
You consider events some bit of delta t over delta v.
Yeah, so as I will try and do this in more details very soon. So the dimension has to be a dimensionless ratio, of course, and that would be some particular characteristic length scale in the system by the speed of light. So that is the thing that would go to infinity. So you think what use are these? And strangely enough, they seem to be appearing, absolutely everywhere. You might have heard a little bit about string theory from Priyadarshini, who was here last term. But we are finding this everywhere. We are finding it in condensed matter systems. We are finding it in black holes, in cosmology. There are fluids, but I could give separate and talks about all of these, and hence a week could run into a month or two. But let's not do that. So what I'm going to be focusing on in this talk is this particular corner, and so we would be attempting to focus this talk on understanding what these weird Carrollian CFTs now are. Why are they of interest for as holographic fluids in gravitational theories for it as that space. So that's the goal of the talk. And just before I go on, so these are people kind of on a long journey, and I would specifically want to mention Shubhitra and Pradesh, who've we've been doing a lot of work of late on this. All right, so with that, let's go to preliminaries, and this is going to be, I mean, a sort of going back a long time. But let's do this slowly, and let's. Okay, so the first bit is what we want to do is we want to take the speed of light to to 0, and this we are going to be doing. So one of the ways to try to understand it is, let's say, if we want to take the non-relativistic limit, then we want to take some mu over c, out to 0. And this can equivalently be thought about as something where xi goes to become epsilon xi and theta is. So this is sort of like what we can think about. And this other one, so this limit is going to be where v over c actually goes to infinity. And this can equivalently be thought about as xi goes to xi and p goes to epsilon.
So the first one makes sense to me because it's like physically you're saying you're looking at things which are moving much slower than you. The second one doesn't really make sense, right? Because we know that time.
Yeah, so this is so at the moment, let's say that these are two algebraically two contractions of the Poincare algebra that I can look at. And let's see where we go. And you are right. You're absolutely right. People said this at first and said that, look, this one makes sense. This is a non-relativistic stuff. Speed goes to infinity. We are familiar with this. What the hell is this? I mean, in the sense that this guy would have something like t prime is equal to t, and x prime is equal to x minus b, right? So this is your non-relativistic, Galilean words. The other one is this weird thing where x prime is equal to x, but t prime is equal to t plus some beta x. It's like, I mean, if you're thinking in terms of xi, something very weird like that, right? And apparently this is just nonsense, right? I mean, what the hell is happening? But let's sort of humor ourselves and go ahead.
But I mean, it could be, I was not looking at physical events and the intervals between them where you couldn't make this, but you could just look at two space-like separate points.
Yes, so the thing is that if the light cones close out, then you can't move.
Yes.
Right? So you can't move and you stay at the same place, right? Yes. So that's what happens. Now the idea is that's true. That's of course one way of trying to understand it. The other way, I mean, which I will actually get to, is what does not if you are. What sort of an observer, if you were that sort of an observer, you would not sort of move. You would only move along one particular axis. That is going to be if you are a null observer, right? So you can't get off the light cone. So this, in a sense, what is going to happen is that these symmetries that I'll do. I mean, algebraic way of trying to understand this. What is going to happen is these symmetries generically are going to appear on any sort of null hypersurface. So just to give myself away, which is why you see all of these applications in terms of symmetries of flat space. This is I should say.
So sorry.
So yeah, I guess I've been slow enough, and this is sort of like just my beginning of the talk. So yeah, so so these sort of weird symmetries are going to generically appear on null hypersurfaces. And that's why these applications do it. I mean, as the flat space, and then these are going to show up generically on even horizons of black holes. And any sort of null surface will actually come this. But let's sort of do the dumb way first. So these will
in terms of that, I mean, if you have a null hypersurface,
yes.
And you can think of approaching it
Yes.
from the inside the cone or
Yes.
outside,
Yes.
right?
Yes.
And if you approach it from inside the
Yes.
cone, you can always choose a frame,
Yes.
right? At least inside the cone where you are at the same time, if I'm right. Which way does it go? No, where you have the same spatial location but at different times, right? If you are inside the null.
So yeah, I mean,
Right? Yeah, I always get confused, but that's correct. Inside the null cone, because delta t squared, you can always choose Lorentz frame where delta t is non-zero, but delta x is made zero. And perhaps you are approaching the light cone like that, so that you have some small delta t. But
let me just sort of elaborate on this a little bit.
Sorry,
Yeah, I mean, since it's here and since since we can sort of go on. If we started off with the Schwarzschild metric, for example, right? And let's say I'm interested in this. Let's draw. But and I'm interested in the null code. So I mean, dr dt in that case is going to be plus minus 1 minus d. So I can over r. So that means if I draw something like this, and if I have this as r, so out here where r goes to infinity, these light cones are just 45 degrees. But as you move in, the light cones, these will shrink. I mean, as long as it shrinks and it's a finite thing, it's just rescaling the speed of light. That is fine. I mean, you can of course, call that 1, call that 5, call that what you will. But when you reach r equal to twice m, this actually just goes to a line, right? This goes to 0, and I will discuss. So this in a coordinate like way is one of the things that you can sort of clearly see that when you approach the even horizon of a generic black hole, you would be able to see that these sort of symmetries are. But let me sort of.
When you look at very far future intersection.
Yeah.
Even there also, go very far in future, any 2 points will be out of
Yes.
Is that another?
Yes, that is another example, and sort of. If you are trying to think about sort of, again, inflation scenario, and you're looking at sort of super Hubble scales, then this is again going to appear there because there you are sort of falling out of causal contact with each other. Separate things are going to evolve without technology. But okay, so I didn't really want to go into this, but the place gets to me and I get to the board and we get distracted.
Sorry, so sorry, I missed, but you will be looking at the speed of light going to 0 limit.
Yes.
And is just in flat space.
Yes.
Is there a physical problem that you could identify if this is relevant?
Yeah, this is the thing that I was trying to show you. this is what we have.
Well, that's great. Can you give me one physical?
Yes, sure, sure.
One, just flat space, no curved space.
Yes.
Some physical problem that I can more easily solve it.
So what I will be saying is,
What I was hoping for was
Yeah.
start with a normal relativistic theory.
yes,
And then some phenomenon in that theory can be understood in this.
right. So what I will be trying to say is that when we are trying to look at, duals to flat space, these are the field theories that that are going to show up.
That's like a
in
cheap answer. I was
Yes.
hoping for something more simple. I'm studying 5 to the 4 theory. I want to compute some scattering cross section, something concrete, some calculation that is live in the field. For instance,
Yes.
if I was in a field in the opposite limit,
Yes.
if I had a massive field theory,
Yeah.
and I was interested in physics, where I've got a few particles and energy above masses, sum of masses is small, then it becomes non-relativistic, reduced to Schrodinger equation. So
Right.
there's a particular situation in a relativistic theory
Right.
where the non-relativistic limit is
That's right. That's right.
and it's
Yeah.
very useful. Let
Yeah.
me some hydrogen atom.
Yes.
Can you give me one?
Yeah, sure. So what I would say is that if you try to look at any sort of field theory, and instead of trying to look at a very low energy limit, if you wish to understand something at very high, high energies, this is something that you would be able
Wait,
to.
so suppose I want to compute scattering in QCD. Is this? Give me something specific if possible.
Scattering in QCD,
At very high energies, or maybe you have.
yeah, this is something that we've not done, but yeah, it would be something like this that would like.
I was hoping for one example where, like in this problem for the relativistic equation, it's
Yeah.
easier to solve once you use the non-relativistic formulation than taking a limit of the relativistic. Is there something like that? Yeah. The Schrodinger equation is a simpler mathematical structure than quantum field theory.
Right.
You reduce to that.
Here, what would happen is, for example, if you started with, box of phi equal to 0. In the limit, what you'll just be left with is del is square of phi. So it will, of course, simplify.
For what question will this be an interesting? For what interesting calculation will this be an interesting? I'm sorry.
No, sure. Let's. So what I can say is that if you, say if you were to think about fluids, for example,
Good.
which are moving near the speed of light.
Fluids moving near the field. Okay.
So one example that we have tried to do is, this the Bjorken flow in the simplified two-dimensional flows. So there, what you can, so what we saw is when we in the original formulation by Bjorken, what happened is there was some phenomenological input which was required, that it had to be independent of independent rapidity and so on and so forth. What we can do here is that we can use the fact that these particular symmetries are going to be the ones which are important to recast that in the language of these particular structures that show up here, and we would be able to get the same equations out, but we will not be able to we will not have to give you these sort of phenomenological inputs. So this is one clear cut, one clear model where we have been able to use these symmetries to actually simplify the analysis. This also then goes to this the next thing where you sort of have
Sorry,
yeah, sure.
from your planning on, is it situations where spatial gradients are very expensive, but temporal gradients are?
Yes.
You want some systematic limit
Yes.
to be able to something like
Yeah,
that.
so for example, all of these sort of new let's have a system where you have bands flattening out. So you would be able to see that these particular symmetries are emergent there, and so we hope to be able to use this there. And actually, in this last thing, what we were able to do is we were able to look at, I mean, a particular region in the liquid phase, which was not understood before. And we were also able to get some mileage out of that.
So if you put relativistic scattering, in a relativistic scattering, no matter how fast you take the energy, it's oscillating as fast in time as in space. At least one way of looking at it is that way, because omega scale. So is that a formulation, a setup that fits into your framework, or maybe I should look at the free propagation with something.
So for relativistic, so what I'm saying is that, okay, so if I'm looking at something where, so I want to be looking at scales which are, I will have to look at, extremely high energy scales, basically, in some sense.
But it's high energy, but let's say I take a very high energy particle.
Yeah.
It's got K and omega, and K is equal to omega.
Mm-hmm.
So there's never a situation where it's oscillating faster in time than faster in space than in time. At least for free propagation. Maybe there's another.
Yeah, I would have to see. What
it feels like highly oscillating from that point of view, right? Or not?
Going back to what you were also saying, that causality is usually sacred, right? I mean, you have
so true. This is true. It's a sector, if you will, of where
so it's some things which are
So you will have to you'll have to frame these things. You'll have to redefine what causality is in some sense.
Sorry. I'm just trying to understand. Will this get interesting physics and relativistic theories, or will we have to go to some weird condensed matter systems to get something?
So what I would say is that if you wanted to formulate, anything on the light cone, for example. So what I would like to do, this is something that I've not done, is the things in the light front and the way that a very high, extremely high energy sector of QCD should be something that where we would be able to find these symmetries and clarify this. In that context, but this is something that we have not done.
In condensed matter systems, for instance, there are these Lee Robinson type velocities.
Yes.
Butterfly velocities.
Yes.
These are not like sacred.
Right.
You could imagine that there are excitations which violate these effective type ones. And then the physics of those excitations could possibly be described. Right?
Yeah, I think there is a very vast range of problems that you would be able to address with this. And but the one that I'm going to try to say a little bit more on is what happens to flat. What are the, so if you wanted to figure out what rules of flat spacetimes are, my claim is that these are the few theories that you should look at, and let's just see what that. But these are all good things to ask, and it would be good to speak about this more as
well. Just to review this one, but in Priyadarshini's talk, she was taking the alpha prime into the string was becoming very big.
Yes.
Okay, there was some.
So
well-defined limit.
Yes. So it is the same thing. So this in that case, what will happen is the symmetries on the worldsheet actually comes because it's a null string. In that, so in that case, so these sort of closing of the light codes which I showed you here will be happening on the worldsheet, and then you use these symmetries to try and see how that sector of very high string theory will. So that's another example. Right. So so I was just going to get to the algebra. Maybe let me just do this here. And so I want to implement this. And in order to implement this, for example, let's look at boosts. So K0I is xi del t plus t del I. So if I were to do the Galilean limit, in that case, what would I do? I would get get K0I goes to. So I will have to scale this. So this goes as 1 over epsilon xi del t plus epsilon t del I. Did I do that right? No, I didn't do that right. Apologies. Did the other way around. So this is going to be, so then since I do not want my particular generators to blow up, I will define GIs as limit of epsilon goes to 0, multiply this out by an epsilon. So I will at the end of the day get, I guess, the P values. And this is what gives rise to this and this transformation. Now, on the other hand, if I took the Carroll limit, in that case, what happens is that the J0I now goes to 1 over epsilon x I del d plus epsilon d del I, and I end up with the other guys, so that I call the CIs. This is the epsilon goes to 0, epsilon times whatever this is, J0I. And I get the other piece out. So this gets xi. So this is the way that you try to take the limits. And once you do that, what you end up with is an algebra. So these are the generators. This is going to be what your algebra is. And crucially, C's would do a 0. This sort of reflects the fact, so this does not close into the rotations like you have on mutual relativistic systems, and this reflects what I call the non-Lorentzian nature. Good. So what you can do is you can look at the extensions of this, and you can add the special conformal and the scaling in, and this algebra is one. Yeah. Good. So, equivalently, what you can do is you can start off with flat space, and then you can take this equals to 0 limit here. And what happens is very clearly when you started off with the metric is going to have a 0. So this we will have some H values out here. The inverse is of course going to have a problem, and hence what we do is we sort of multiply this out by C squared, then we get a 1. So what would happen is that these particular degenerate structures are what are called these Carrollian structures, and these are, so you will have some H mu which has a 0 in it, and you will have these thetas which this particular relation will. So this is just flat space, and what you can do is you can sort of generalize this to and curve space times as well. And so you will have an H out there as well, and there will be theta which is one.
Just sorry.
So this is just.
Any structure, is it? I mean.
So this is going to be, so the structure, so the metric will be placed by both of these. So that is, that is what is.
So these are mean,
So just that, so the fact that, this particular big theta is like 1 kilo.
Projector of the time.
Yes. So if that's all frame that you can choose. Yeah. So if you looked at what the algebra of this, so you can find what the isomorphism, the isometry algebra of this structure is, and then that is going to give you the algebraic things that I did in the last. So this is the geometry behind the structure that I showed you in the last. So if you wanted to get to what the conformal version of this is, then you would again have to have some these would be the conformal isometries would reflect what the conformal Carroll algebra that gave you. So that's sort of like the geometric way of trying to do things. But now let's sort of change gear and look at something else. All right, so this is so we want to now focus on flat space, and we want to look at what the asymptotic symmetries of flat space. If you so these are going to be given by the one-dimensional subgroups in three-dimensional flat space. The algebra looks like this, where these so these ends are going to be super translations. So what are these super translations? These super translations are angle-dependent translations of the null direction. And these L's are ambient super rotations. These are in 3 dimensions, the flows of the circle at infinity. And Barnes and compared in 2006 found that there could be 2 central extensions here. For Einstein gravity, this particular extension is 0, and this one is 3 over G. And this is the BMS algebra in 3 dimensions. Okay, so what's it in 4? In 4 dimensions is a little more involved. There are, 2 copies of the grid algebra and the super translations act. These have now, 2 indices R and S, and which are under the left movers and the right movers here. And we will not speak about central terms. This happened. So,
sorry, I'm sure you'll come to this, but if you start with some more familiar situation by contracting it, you can come to.
Yes, I will get that in just a little bit. Yeah, so why am I saying all these things about these separate algebras and so on? Who cares? What happens is that the conformal Carroll algebra in D dimensions is isomorphic to the BMS algebra. Good.
From the BMS point of view, the L's generate translations along the right.
No, so let me just clarify that. So the super translations are the ends.
Oh, okay.
Okay. So these are the ones which are going to generate translations of the null direction, but they will also have the L's are the S1s and so the L's are the ones which are the diff S1 in the 3-dimensional case. Yeah.
And I'm sorry to be so ignorant about all these matters, but sometimes there is a map from what happens at sky plus and minus to what happens on horizons. And
yes,
is it true that if you similarly look at, to go back to one of your motivations, I don't know, motivations hugging the horizon?
Yeah.
You try to think of symmetry terms, you can similarly cast things.
Yes. So those algebras again, I will, as I said, we can go on for months and months on this. But those algebras look very similar to them. But the super translations, it's not quite there, but it will fall under the class of these, conformal Carroll algebras, which I said. But there is one little catch, since you sort of pointed this out, let me say this. So you see that when I write down this particular way of trying to do this, and conformal isometries in general could have had a lambda 1 here and a lambda 2 here. I choose this in a way such that in the bulk, what will happen is the generator, the scaling of space and time would be the same. But you could sort of generalize this to what are called n conformal Carroll algebras, or something with your more familiar thing about a z exponent, basically. So what we would be able to see is that the horizon. So what people have found is that the horizon symmetries here have z which is not equal to 1. So these are again going to be conformal Carroll symmetries, because it's a null surface after all. You would not be able to go. So that has to be there. But how these things will scale, that might also depend on what particular boundary conditions you put in. But the ones that people have used lead to subtle difference. Yeah.
This conformal Carroll algebra is the limit of the usual conformal algebra?
Only when z is equal to 1. Okay. Yeah. So this okay. So let me try to clarify this a little bit. I don't think I have a slide with this, but so as I said, L psi. So the Carroll structure is H mu and theta mu, right? So this L psi of H mu equal to 0, L psi of theta mu equal to 0. This gives your Carroll algebra. Okay. L psi of H mu equals to lambda 1 H mu. L psi theta mu equals to lambda 2 theta mu. This gives you conformal Carroll. See that these two are not the same. We can call something which is lambda 1 by lambda 2. You can't get this wrong. Is equal to some minus here, minus n over 2 watts, minus z or something like that. I'm going to get this wrong, sorry about that. So if I take z equal to 1, that is the limit that I showed you earlier. But if I do not take z equal to 1, then I will get a larger class of these guys. So that's the answer.
But is it finite or not? Because it seems like the other, you said 2 are isomorphic, but one of them was infinite.
No, you are right. So all of these are going to be. All of these are. Going to. So I had a line in this previous slide which said that you can give this an infinite dimension with small dimensions. So things matter.
So in the case where it's a limit of the normal conformal algebra,
yes.
This algebra is some symmetry of correlation functions and some range of cross ratios then?
Yes. So I will use this to find out what the endpoint functions etc. are as well.
Yeah, but I was asking, take a relativistic conformity.
Yes.
Now, are there some range of cross ratios, ordinary cross ratios of the relativistic conformity?
Yes.
In which the correlators obey your constraints.
Right, so you want to start off with something which is a relativistic CFT,
Right.
but instead of trying to take the limit at the level of the algebra or at the level of the, so what I can say, yeah, so it's a little more involved because in the, I mean, the two-dimensional case I will show you, it's that the in this I mean high energy limit, the highest weight representation will not go. I mean, go into highest weight representations in the at the equal to 2 case. So it's a little more, I mean, involved than.
I think.
But-
I was expecting you to say if you separate operators so that the time separations are small compared to space separations, then the usual symmetries
Yes,
of the usual constraints of
yes,
conformal
that is what I would have said if not for this. I mean, twist in the game a little.
But let me not even worry about
Okay.
just take a correlation function which is a number.
Yes, yes,
Some 4-point function.
Yes.
A function of z and z, but not
yes,
z.
yes, yes.
Not
Sure.
the normal cross
Yeah, yeah.
Now I look at it in a region
Yeah.
which I can think of as being all times very small separated.
Yeah.
But space or am I doing the other way around?
Actually, I think
Yeah.
the other way around. I mean, he seems to allow for time.
Yeah, so if you were to place, if you were to try to, I mean, look at a CFT and try and place it on place it, I mean, on a null
I'm not
surface.
placing it on anything. I'm taking
Sure.
normal CFT.
Yes,
I'm looking at some particular
Yeah.
kinematics for correlation function.
okay.
I can choose to look at correlators in
Sure,
orbit
sure,
such that they
sure.
separate large in time and small in
Yes, I would say that this would,
Now,
I mean, module the problem of the representations.
No, I don't
Yeah.
have I have a number.
Okay.
4-point function is a function.
Mhm.
Okay, it obeys a what identity.
Sure,
Okay, now I can study that what identity
yes,
and look to see if it simplifies or does something nice
yes,
in the limit here.
sure.
And will it reproduce some what identity that you are independently able to derive?
Yes. So, I mean, for example, this is, I mean, way at the end. So I mean, all the soft theorems, for example, are things.
I'm so sorry.
Yeah.
You're doing much more complicated than what I am. I'm just taking normal 4-point function.
Yeah, absolutely. You are yes, yeah. So yeah, okay,
Okay.
yeah.
Why do you expect something like that should be the case?
What? I
Why
was,
do you
it would not be the case you're saying, Abhijit?
No, I'm just wondering. I don't see. I mean, why should something like that be a case that it's in some particular region of kinematics that you would get this symmetry? Because I was wondering, whatever configuration you are proposing, all the other configurations related to it by conformal symmetry would also have that.
That will not be valid, you're saying. But I was thinking that
I don't know.
since
No, I mean, what I would say here is that when you are when you are, I mean, strictly, I mean, in the limit, your I mean the symmetries will change, and I mean, and the word identities, I mean, would actually go into that basically.
So what is that limit?
That is going to be, I mean, this I mean, t goes to epsilon t, like.
But maybe this.
So that's trying to put the CFT on, I mean, on a null surface.
But suppose I take a normal CFT.
Yeah.
Put normal Minkowski space.
Yes.
Nothing funny.
Sure.
But I just look at insertions.
Yes.
Such that all time separations
Yes.
are very large compared to all space separations.
Yes.
I mean, this doesn't sound like a very invariant statement,
Mm.
but maybe it is. Maybe it is in some way. Okay. So it's basically there's one line.
Right.
One time-like line, and all insertions are arranged around that time.
Yeah. So that is what I was saying. If you're going to try to look at, I mean, something like a null limit, where you're close to the light cone. If you have operators which are close to the light cone, this t goes to epsilon t essentially does that for you. It is going to boost your system, and this is like an infinite boost of your system.
Okay, so suppose I take one time-like line.
Yes.
So one time-like line, I arrange all my operators in the neighborhood of that one time-like line.
Yes.
And make them close and close.
Yes.
Okay, now this is some limit of cross ratios.
Yes.
Now, the question was, if you take the word identities in this limit,
Yes.
do they reduce to what identities you would get directly from some other point of view?
I would, I mean, this is you know, computation which, I mean, which can be done for sure.
So let
Yeah.
me ask the question just a little
Yeah.
bit different, right? Suppose I start from the usual conformal.
Yes.
Right? SOP command.
Yes,
Is there a way to take systematic contraction along
Yes.
the lines of what you were describing
Yes.
here for J0I to
Yes.
come to a algebra
yes.
which is a kind of Carrollian conformal
Yes.
algebra? Right?
I mean, of course,
Because
of course.
I'm just thinking, if that's the case, then I take the same limit on the correlators, more or
Yeah.
less they will meet the corresponding invariance conditions of what I did.
Right,
So that's
then-
perfect, no?
Yes.
So, I mean, if that is the
Yeah.
case, perhaps that is the sense.
So that is, yeah,
That's the limit where times are much larger.
I think so, that's
Yeah,
what it describes.
yeah.
So basically, you choose one line that is timeless.
yes,
You address your operators around that.
Yeah.
In that limit. So this is something now, this presumably, unless Abhijit says I'm wrong, can be worded as a statement about cross ratios.
Mhm.
In the common field theory. So it's some statement about some limit of cross ratios, very Lorentzian cross ratios. These are not cross ratios that you can get in a Euclidean space.
no, you'll not,
Yeah.
because it requires the,
So
yeah,
Z is not complex conjugate of Z bar, Z is Z bar.
Yeah.
Independent numbers. But some limit of cross ratios where you've got another structure which may be similar.
yes.
That sounds interesting, and I was wondering if you can use that to say something about, okay, fine, I'll shut up.
No, this, I mean, I like this, I mean, of course, but all that I was trying to say is this whole game about trying to understand things, I mean, which are near the light cone. You know, I mean, the light cone sort of limit of I mean, of the OPs and these light ray operators, etc. I believe can be recast in this way as well.
Well, what would be interesting, Arjun, is not just recasting it, but to get something new from this perspective.
Absolutely,
Conformal
absolutely.
theory over the last 20 years has been studied
Yes.
so thoroughly.
Yes.
Can you say something new or more easily than you can otherwise? That's
Yeah, sure. I mean, all I'm saying is that trying to define field theories, I mean, on a null surface has not been looked at in a great way. And for example, I mean, if we sort of think about say Rindler, and we say the stress tensor would blow up, I mean, as we sort of near the horizon, etc. If recast in this way, in that case, what we would be able, what we can show is that things do not blow up. You just have to, take the limits in the right way, and then it will start to make more sense.
Thank you.
Yeah.
Like it's getting this infinite extension
Yeah.
along the line of the does that also, like if you take some limit, somehow you get this symmetry or?
Yeah. So in the in this limit, you are going to get an enhancement of symmetries. Even for, let's say, if you started with b equal to 3 or 4, whereby the conformal algebra itself was a finite dimensional algebra. In the limit, you get more of these structures out, because it's a null structure, right? So that is why you're going to get more out of the system, more symmetry out of the system. And yeah, so that's yeah. So in a sense, the thing that I'm supposed to, if you're thinking about flat space in four dimensions, yeah, you know that up at the null boundaries, there's a different dimensional BMS symmetries. These can, if you were to look at what what the limit from say maybe a CFT was, you would be able to sort of follow that through and find that there's more structure out there which you can use, basically. But yeah.
Sorry, Arjun, one
Yeah.
question. I've
Yeah.
got disconnected for 2 minutes, so maybe you discuss that.
Sure.
I was wondering that if you, this light cone limit, this light-like approach that you were talking about, maybe
Yeah.
going back to Shiraz's comment, maybe it is kind of, telling you about the symmetries of what is called the light cone limit of the correlation functions. And it is
that is what I was trying to say, actually. That is what I was trying to say, that it may be possible to recast, the light cone operators, the light cone OP in this, enhanced symmetry structure which you get from here. This is again something which is not being
because
done.
also some people have studied these light-like
Yes,
cone
yes.
limits and realized that
Yes.
there's probably some enhanced symmetry
Yes.
that governs it, like Parnachev and so on. Right,
Yes.
some sort of a, where you can talk about multi-trace exchange of gravitons and so on, which is
Right,
like
right.
higher Virasoro type things.
Yes, yes,
I mean,
yes.
this
So,
is just very far out, but could it be that it is related to that?
I will almost be willing to bet that it is this, and you're going to get these same structures here as well. But this is a problem that I've not done, so I cannot give you a yes or no answer at the moment.
Okay, thank you.
You must remember, seems to me physically, I could be wrong,
Yes.
that this is the kind of symmetry that would be useful for a highly boosted observer.
You are
Yeah.
absolutely right.
And just to go back to
Yes.
your black hole example,
Yes.
it's the Ringler observer, very
Yes.
close to the horizon.
Exactly.
Whose time takes but space doesn't.
You're absolutely
And
right.
so it's an unfamiliar limit to us because we don't normally go into highly boosted frames.
Yes.
But perhaps if you did that.
Yes, and you can actually clearly show that as well. You can start off with this, say CFT and boost it. And if you, apply this, an infinite boost on this, you would be able to see, your CFT is defined here. So you boost it, it goes here, and it goes there. So it is the light-like boost that we are interested in.
It's that.
As you reach the light-like boost, as you hit this, these symmetric structures will emerge, and this is something that I can actually show you.
Okay.
So that's the thing. So
That seems like you're physically right.
Yeah.
It's like a modular operator in the end at the horizon.
It is at the horizon, exactly. Yeah.
Yeah, that light cone quantization behaves non-relativistic.
No, that's a wonderful question.
Yeah,
Which
yeah. I had the same thing for a long time going on.
now, I have an answer to that, which I can give you, but then I will not be able to do this talk. It's not.
I don't know what exactly.
The light cone quantization, as you said, this is what I was going to just say, but since you said it this way. So if you look at, this is just that's. So if you try to look at what, so there are. What do I do? So if you take the Poincare algebra and you write it down in terms of light cone coordinates, this is something that has been known since the 1970s. Kyle showed us that you are going to get a lower dimensional, non-relativistic subgroup of this. What was not known earlier is that you also get a lower dimensional Carrollian algebra, two of them. And you can show that there, if you were to focus on the light directions, these are the algebras. So you do one particular contraction which will sort of focus you on the light directions. Then your Carrollian algebras will appear. If you do it on the transverse directions, then your non-relativistic algebras would appear.
It's about you take US time or VS time.
Not quite. US time and VS time give you two separate copies of this, but there are separate subgroups which appear here actually. So so this is something that I'm happy to try and more about.
Just one.
Yeah, yeah.
Because I was thinking about the same.
Yeah,
Yeah. So if you boost very fast.
Yes.
Because of time dilation, everything moves very slowly.
Yes.
Is that the opposite to what you're saying?
It is going to be dependent on if you are going to look at yourself, or
Everything else.
if you look at everything else, you're right. If you look at yourself, that is not right.
Okay.
Okay. So that is the point of view. So you need to separate out. So there are, in a sense, two light cones here. There is a transverse light cone and there is a forward light cone. Okay. So what is happening is that if you boost this gets smaller and this grows larger, right? So this is the non-relativistic way of trying to understand it. This one is going to be the ultra-relativistic way of understanding it. So that's what that is about.
I mean, I was thinking if you have the Rinder observer,
Yes.
very close to the horizon or whatever, then as he goes along,
Yes.
right?
Yes.
His clock, of course, ticks at
Yes.
whatever it is.
Yes.
And that's the Hamilton, that
Yeah.
was the relevant time
Yeah.
interval,
Uh-huh.
right? Yeah, and then you're right. I think some light rays get to him very late.
Yes.
Right?
Yes.
But okay, he has some time going along. Okay.
So so we need to figure out how we want to do this actually. So because
The speaker speaks only for a small. This is the golden rule of Hassan.
No, this is wonderful. This is wonderful. This is why I'm here. Because I was sort of looking forward to doing this. But I have like whatever. I have like about 50 more slides, which will take about 7 more days, I think. So let me sort of give you a little gist of what we were. So this is not new stuff. As you can see, this is 2012, etc. So what I was trying to get at is that these very weird theories naturally appear when you are trying to look at duals of flat space. Now, one thing that so the idea essentially was, so if you were in three-dimensional and this is the spacetimes, we know that there are two copies of the Virasoro algebra. The limit to flat space is the one that is boxed out here. Now, this limit, if you do this, then you started off with two copies of the Virasoro algebra. You end up with the conformal Carroll algebra, or if you wish, the PMS algebra that I showed you in the last slide. So this is a limit that we can follow, and then you can also see that if you took these central terms and C equal to C bar, so this is ADS3. These are the Brown and central terms. So CL will be 0 and Cn will be 3 over G. This sort of reproduces what was done from an intrinsic analysis. So this was that. So what is what I call the Carrollian road to Minkowskian holography? So the field theory, so we want to say that the field theory that is dual to these flat spacetimes should inherit asymptotic symmetries. So for D-dimensional asymptotically flat spacetime, the dual should be a D minus one dimensional theory. But now this is going to be these weird sort of Carrollian field theories which live on the null boundary of flat space. So we have two ways to try and understand them. We can use only these symmetries, but we can also understand them from the limit shown. And this is what we have been trying to do for a long time. Just to give you, this is not very useful, but this is the stuff that we've been doing over the last decade or so. We've been trying to match things on the bulk and the boundary. And there's been a lot of work on this. And this is mainly three-dimensional bulk and two-dimensional field theories. What I had next was a brief review of
Just, you must go on, but just briefly, what is the statement? If you take three-dimensional asymptotically flat.
No, I'm making a bold statement. If you take D-dimensional,
I mean, okay, take D.
yeah, D-dimensional, I mean, asymptotically flat spacetimes, then my dual theory is going to be a, I mean, 4-dimension one. So that's a D minus one dimensional field theory. This is going to live on, I mean, on the null boundary. And so this, since we know this, I mean, the zeroth law of holography, if you wish, is that the symmetries in the boundary and the symmetries on the bulk have to match up. So that means that the field theory that is dual to, I mean, say, a D-dimensional flat spacetime is going to be a D minus 1-dimensional Carrollian CFT. Now, just to sort of clarify this a little bit more, let's take a bit.
The Carrollian group is the same.
Exactly. Yes. So that's the sort of, I mean, $0 statement, and so that's, and we will build on this. So in the 3-dimensional case, we have tried to use this interdimensional symmetries as well to get some answers which match from the boundary and the bulk. But the more recent work that we have been trying to do is built in 4 dimensions. And let me actually skip to.
Yeah. Just, I'm particularly interested in 3D at the moment.
Okay.
Is it the case that there's a precise statement of holography now in 3 dimensions in asymptotically flat spaces? Is there a precise statement? I can compute all bulk quantities by doing this in your Carrollian field.
We have calculated, I mean, stress tensor endpoint functions, and we have been able to match them from the boundary and the bulk. We have calculated, I mean, bulk entropy, and we have been able to reproduce it on the boundary. We've been able to get something like a dynamic entropy.
Can you put in, and then you should,
Yes.
can you put in matter in 3D and have an S matrix and obtain that from a boundary calculation?
We have done this in the 4-dimensional case.
Okay.
The 3-dimensional case is something that we are trying to look at. I will give you the 4-dimensional case, but that's the part of the talk which I wanted to focus on, because the more the popular way of trying to do it is by saying that 4-dimensional flat space is dual to a 2-dimensional celestial CFT, which lives on the celestial sphere, and there is a map. So what I've been harping on for a really long time is that, look, it shouldn't be 2-dimensional, it should be three dimensions. It shouldn't be a relativistic CFT. It should be this. And the reason why I keep on saying is, I mean, as I said, the zeroth law. I mean, in the sense the symmetries on the bulk and the symmetries on the boundary should match up. Flat space has translation symmetries. So it's ISO 3.1. It is not. I mean, it's not just the SO group. There are translations that you have to encode, and the punchline to give away everything is that if you include translations in a covariant way, you are able to get much more out of it, and there are some features that at least I find a little unattractive about the 2-dimensional formulation, which if you do it in the 3-dimensional way, gets solved. So maybe I can give you an idea of that going ahead. Yeah. So let's skip the ancient history bit, and let me move on to the more recent stuff. Okay, so how long do I have? I'll base my this. Enough. Okay, good. Should I go back to the 3D case then? Maybe you guys will give me 2 more hours, who knows?
No, because of lunch being a cutoff.
Lunch is a cutoff. This is why you have it at 11, because lunch is a cutoff. Otherwise, nobody's going to go home. All right, so All right, so there's been recent resurgence of physics in that space due to this IR triangle by Andy and friends, where you have this usable emerging story about linking up soft theorems with asymptotic symmetries and the effects in this really nice way. So just to remind you. The asymptotic symmetries in 4 dimensions is this ugly looking algebra. And there are these are the super rotations. These are super translations. The super translations, as you would remember, are translations of the null direction. So let's say square plus. And that's U. And there is sphere here now at each point. This is M2. And so super translations are translations of this U direction that depend also on the angles. And the super rotations are going to be, we are going to be using the version of Varnish and Trosaw in 2010, where you do not give this a lift to the full diff S2, but you look at the generalization to the full conformal.
In RS, RNS are slightly harmonic kind of level?
No, these R and S are the things which will go with, so the R is is the one which moves the moves the holomorphic guys, and SR is the one which moves the anti-holomorphic.
So is that the super translations were space dependent translations?
Yeah, so it will be on the theta and phi.
So presumably these RS are some Fourier.
Yeah. So you would be able to write this as something like which is a IR. I'll get myself.
RNS parameterize a complete set of functions on an S2. If you range over all RNS, you range over a complete set of functions on S2.
Complete set of functions on S2. Yes, I think so.
Okay, so very long.
Yeah, it's translations which depend on yeah. So roughly, yes.
I got this very okay.
So okay. So there is this is blah, blah, blah.
Sorry.
Yeah.
So super rotations are what exactly? They're not rotation.
Yeah. So these are let's look at the 2-dimensional the three-dimensional thing, which is going to be a little simpler. So in that case, so that is MR. So this is
this is super translation.
Yeah. So this guy is super translation. So this is I some R theta into some M del U.
Yeah.
But this the super rotations are just usual. So yeah, let's maybe call this C. Okay, so this is a stereographic thing. So that's yeah. So yeah.
Right. Okay.
So that is going to be the diff of the S1 in the 3-dimensional case.
Yeah.
In the 4D case where we have an S2, you could have also gone into the diff of the S2, but we are not doing that. We are so there is going to be the normal rotations and translations will be 10 basically now. And boosts, of course.
Yeah.
But these are ones which will have more. This is so the global part of it is going to be just the global. These six guys, right? So L0 plus minus 1 and L0 plus minus 1. These are the usual ones, the usual sort of 3 boosts and three rotations. But now you also are going to enhance this to the full two copies of the Witten algebra basically. So these are, I mean, so, I mean, these will be generalizations.
From some particular asymptotic.
Yes.
It's not just that I think of the sphere S2 in terms of Z and Z bar and
Yes.
I construct my LNs and it's not.
It is that, but it also, so you, I mean, if you were to just, so, you know, the point is that when you are in four dimensions, you would not be able to find, find sort of, find proper boundary conditions, which will just restrict you to this. So if you do this, asymptotic symmetry analysis, then the boundary conditions that you'll have to put to, for example, include both black holes and say gravitational waves would not allow you to restrict to just the Poincare group out at infinity. So you are going to get this infinite dimensional enhancement where the super translations are going to be there. Now, how and why you're going to be extending this, other part of it is sort of up to you and sort of on the boundary conditions you use. But yeah, so that's the thing. All right, so yeah, lots of words on this slide which are not useful. So the idea is that there's been as I was saying an attempt to understand it from point of view of two-dimensional dual field theory. What we are trying to propose is that we need to not neglect the null dimension. So that's what we are trying. So let's have a very quick lightning review of celestial holography, whereby I think there is a slide which is going to do a little better than this. Let me try and find this. Yeah, okay. So you start off as I've tried to write down here. So so the observables in this case are S matrices. So if there is a holographic dual, then this must compute endpoint bounds basically. So we look at a particular parametrization of these mediums, and we are going to be looking at massless particles. So these are going to be expressed in these three coordinates. So Z, Z bar are going to be this geographic coordinates on the sphere. So what are we trying to do? So what the main point is, when you look at Lorentz transformations, these are going to act like global just CFT like transformations, and the Zs will transform in the way that you. So the main input was that when you are looking at these endpoint functions, it's more interesting to look at it in basis which is not the same as a so you Mellin transform these guys. And so then just to get back to so what you can show is that so when you do this, you will see that these Mellin transform amplitudes transform like endpoint functions of two-dimensional CFT. So there is a relation between 2D CFTs and 4D scattering through this program. Going back, okay. So this is what I've been trying to just say here, just saying all of those things in one definition. Okay. Yeah. So again, so that's what I was saying. So this So these objects, these O's, I mean, transform, under rotations and boosts in terms of, fragments. So you can recast scattering in 4-dimensional, asymptotically that space-time in terms of endpoint functions of a 2-dimensional CFT, which lives on this. Very good. So what do I feel is a problem? The problem is that the isometry also includes translations. So where did my translations go? So what happens is something weird. If you started off with a translation and these particular operators, which I just showed you in the slide before, if you hit it, if you translate it, say let's look at a time translation right now. What you will see is you end up with something. Ignore this factor for the moment, but you started off with an operator which had weight h and h bar. You end up with something where the weights of the operator have shifted. So, you can also do it for the the PIs as well, and there's going to be a similar thing. So the weird part is that the operators change under the weights of these operators change under translations in the bound, and we find this unattractive feature. And also, this I wouldn't have time to go into this, but the Menon transformation as it stands is also also singular. For 4.6 graviton amplitudes in the bulk, it leads to something which goes up.
Not for Virasa.
Yeah, but for the 4 graviton amplitude.
Oh, hindsight 4 point.
Yes.
Not
yes.
4 point graviton.
Sure.
And he sometimes likes to say that this may be a feature. Just
Yeah. So, I'm
not saying I believe it. I'm just putting it.
Yeah. So really trying to be so ignorant. What is the significance of the Mellin transformation? The physical S matrix is related to the correlators through a Mellin.
Yes. So let me just do it. So it's yeah.
I guess.
Yeah.
Okay.
And Mellin transform is like Mellin transform over all energies. He has important contributions from the. This is why Einstein gravity doesn't.
Yeah.
Okay. However, in string theory, the sort of feature, yeah. So the Mellin transform is well defined. And he sometimes likes to say maybe this is going to be eventually a principle. Not that there's much evidence for it, but just to say.
That is why I sort of said that there are. I should write some of my issues with celestial holography. Maybe it's not an issue.
Okay, you can't adopt an effective field theorist perspective. So let's say I'll do the Mellin transform with a Carroll because that's all I care about.
Yeah. So which is what we will get to, and this is something where we will actually. Another thing which I personally find a problem with. Again, it may be fine, but I think of this. So if you started off with flat space, and as we were trying to do, we took this infinite. If you started off with ADS, I'm sorry, and you took this infinite radius limit of ADS, you get to flat space. The flat space does not. If you started off with ADS 4, you get to flat space in 4 dimensions. You don't get to flat space in 3 dimensions, for example, right? So you would also expect that flat space holography, at least some aspects of it, would appear as a limit of much better understood ADS CFT. Since flat space does not reduce, it's unlikely that the dual field theory should also do the same. From this perspective, it's more natural, if you wish, at least to me, that we would expect this to have a codimension one one sort of holograph like ADS CFT, and not I mean, a co-dimension tool. But again, this is what I feel, I guess. All right, so let me say is that with the way that we are trying to go about this, we will solve the so-called problems, if you wish. I should, put that in quotes. But the main message is going to be we will have to keep track of it. On sprites, right, classes, primes, you see keep track. All right, so this is work from 2022, and yeah.
Sorry to interrupt.
Please. Yeah.
Sometimes people do these talks on flat space holography and they're working on the S2, but they include the generator for translations along you. Well, then they've included all, the information. Here, here are you saying we'll be more explicit in a sense?
I'm just saying that they include that particular, so it's like, it's like saying that these particular generators exist, but my field theory doesn't have them, which I find a little problematic. So what I would be showing you is that this particular, if you started off with the field theory, that's it may not be the field theory that we like, but it's the field theory that we have got. So if you started off by including, let's say, let's drop the infinite dimensional blah 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 for now. Let's just think about I want to realize holographic dual for flat space in four dimensions, and let's say I'm sort of being stupid and saying that Poincare invariance is all I like. So it's ISO 3.1 in the bulk. Can I have a field theory which is in 3 dimensions, which also is going to be ISO 3.1? So that's all I'm going to be doing. And if I do that, you will see that this weird thing about translations, shifting weights, etc. Those are the things which will not be there. Okay. So Shomik's work in 2018 is something that was so he was doing this in 2018. I was doing something separately a little earlier, and we then realized that we were doing the same thing, but approaching it in ways which are not quite the same. So what did he do? He tried to look at these particular operators, these that I just defined in the celestial CFT, but he translated. He looked at something which had an explicit U dependence. You just take something which was at U equal to 0 and you translate the damn thing. So in terms of what happens on the other side, these were Bellin transformations. So you do this, and what you end up with is there is an exponential IU piece which sits in front of the case. So this new field is the evolution of the usual celestial field, and it's not defined only on the S2, but on the whole of the structure. Now, if you were to just go back to this work here, you would be able to see that the transformation of these fields are is this. So it'll transform it'll have the usual sort of transformations that I showed in the last slide. But what is going to happen when you translate it as well? That only the U is going to shift. These H's are not going to shift. So let me try to sort of clarify this a little bit. So this just shows that if you are doing a bulk translation on these fields, what used to have weights H and H bar also stay H and H. Okay. So let's try to understand this a little bit more. So this is what we were doing earlier, and we started off with the algebra. So this is a sort of vector field way we are trying to write this algebra. So you see these are Z bar, Z and Z bars. What we will do is we will label the operators with H and H bar, and we will implement the high weights. This was already done in the two-dimensional way. What we are doing more here is we are going to also, so these will be highest weights of this whole algebra, not only the, not only the width subalgebra. So this is the extra weight. So then you can find out what the transformation rules of these primaries, the 3D primaries in this case are. And then you will find that it is the same as what he had proposed earlier here. Okay. So what is happening is that when we look at the shift, when we are going to be looking at the fields which are defined not only on S2, but on the whole of U, you get that translations act in a nice way. And that translates to the highest weights of the entire algebra. So it's also this guy, which is crucially there. All right, good.
So you didn't now have a shift in weights.
Yes.
You just had a translation.
Yes. So I've just included this. I've just made this a three-dimensional field. That's it. So when you move on to how you're going to map between the endpoint functions of this. Now, crucially, you get these extra IU factors out there, and this is what Shomik called the modified transformations. And so this is so this transforms. So these are the left hand side right now are now Carrollian primaries in 3 dimensions. So endpoint functions of these objects are going to be related with the S matrix. So this is the what we propose as a co-dimensional one for the system.
So one thing
Yes.
I should have asked earlier, you didn't have any central extension in your algebra, right?
Yes.
And seemed a little strange to me.
Yeah, so
That's
this is so at the moment whatever we are doing is without trying to understand the central extension. So for the 3-dimensional bulk, 2-dimensional boundary, we had central extensions that were fine. For the 4-dimensional thing, this is a beast basically. This is a beast which is lurking somewhere, which we do not quite understand. You can give the Virasoro central extensions, but if you go back, sorry about going back so long. Yeah, so here, if you were looking at 3-dimensionals, then you see you could have had both CL and CM, and this CM is the cross thing between super translations and super rotations. When you think about Einstein gravity, this guy actually goes away, and this guy stays. Now, if you were looking at the 4D example, you can of course add central terms here, but closure of the algebra, etc., will not allow you to add things here. So there is Glenn Varnish has a lot of work on this, where this becomes not a Lie algebra but a Lie algebroid, and hence you can add some very field dependent central terms. But I don't really quite get that, and I do not quite yeah. So
But anyway,
at the moment we are not going to be looking at central terms. We are going to be just looking at the Poincare subalgebra. For this. But I think it's an important thing, because if, like in the 3D case, we want to have a sort of Cardi-like formula which is going to reproduce something and so on and so forth. Of course, we would like to have a central term. But yeah, so that's something. So, but there have been claims in the literature that the central term is going to be 0 as well. So yeah, so there's a lot of things in the literature which are not very well set.
How do spatial translations act on your ZMU coordinates?
Yeah, so hopefully I have this somewhere written. Translations on the Z and E. So you, so my, yeah. So the translations of the fields will shift U and not shift Z.
So so translation has some direction.
Yeah.
How does that affect the shift in U?
No, this will be, this P, Q, and R. I mean, if you are doing things with, I mean, only with U direction, you get a P.
What is P?
P is,
I have a translation vector.
yes.
Where I was wondering where that vector index went in.
No, so what I have done is split this up into this stereographic Z and Z bar as well.
Nice.
So it'll just so PQ R and S.
So Z and Z bar are like a unit vector direction.
Yes. So
the change in U is by dotting with the translation dotted with unit.
Yeah. So let me just say
Z and Z bar like a direction unit vector.
yeah, here.
Now if you translate in some direction, there's another vector. You take the dot product.
Yes.
That determines.
So that's the end, if you wish. And I choose to
and it's that dot product of the translation and this n that appear in the shift in U.
yes.
So the shift in U is then dependent. That's the sum.
Yeah. Okay. Very good. So what is the
and the fact that the translations don't act on Z because that's just an angle seen at infinity. And a finite shift here doesn't change the angle. Because then infinity.
Right. So what we are trying to say is that the Poincare group of 4D AFS acts like the 3D, conformal Carroll group at null infinity. This is exactly the same. This is the analog of the statement that the Lorentz group here would have acted as the two-dimensional relativistic conformal group at null infinity. Now we have just included the translations here as well.
So translations act as a particular super translation.
Translations act as a particular. There is a sort of so the translations. I mean, it's
It's just you in some Z dependent way. Wasn't that what you call super translation?
Yes, but yeah. So there will be so there will be a del U, but there are also del Zs, right?
Did you tell us the translations didn't act on the Zs? If you just go back here.
So
changed. The formula.
Yeah, right. So what I mean, okay. So let me get this right. So the
is like even a finite shift will you can see even a finite shift in time pattern.
You can see a shift in U, but not a shift in N.
Yeah.
So you won't translate Z.
But yes, exactly. So spatial translations won't be anything.
Neither space nor time will change Z. Z will be unfair. So then it's just a shift in U and a Z dependent.
Yeah, it's a shift in U in a Z dependent.
And therefore it's a super translation.
Yeah, I'm just trying to I'm just getting a little confused because of the fact that there is going to be for example, there has to be a del Z sitting somewhere.
Yeah, that's
no. So the thing is that when you are going to write down, for example, what the what L's. So these L's are going to be so Z to the n plus 1 del Z, but there is going to be
why is there
n plus 1 U Z to the n del U is here.
No, but why is there a Z? And that sounds like saying Z is changing.
This is in
This is-
These are your
Yeah, these are my super rotations.
No, I'm asking what translations?
Yeah, so what I'm just trying to just get is, there are, yep, so that's that, of course, yeah, the mapping is a little,
The main thing that we not in that, if you have rotation in space, but you will have.
yeah, so that is this, no, I mean, you are right. So there is a, I mean, the thing that is happening is that I've written it in Z, so you know, if you do the thing in X, Y, you know, Cartesian coordinates, there's a map. So yes, I mean, you are right, all the M's are going to be my translations, yes. So that will not, you know,
Spatial translations, finite spatial translations cannot do anything. Okay? Why would they even translate around the boundary? I mean, time translation, T minus R.
so you have to,
This U is a boost direction. So it's a mix of space and time.
Yeah, T minus R.
So the part of your spatial translation that mixes with that space will shift you.
yeah, it's just that, you know, I mean, you could sort of write these things down in usual Cartesian coordinates or in spherical, but you have to
I thought
change to,
angular direction.
There is an angle direction.
Yeah, so
yes,
like translation along like finite, let's say I'm shifting x by x plus delta x. At infinity, this you're also dividing by the
Z is not going to change.
no, Z will not change.
Z will not change. You will change.
You will change, but you will change in a, you know, I mean, the Z, I mean, so there will be Z pieces, there will be Z bar pieces, there will be Z bar pieces, basically. And you just have to, you know.
Wait, but just was it right that translation is a particular example?
Yes, you are right, yes. Yeah, I mean, translations in the bulk.
Translations in the bulk is a particular super.
Yes,
Okay.
yes. I'm sorry about that. I just want to make something. Yeah, okay, so, and what I was saying is that the 3D, you know, Carrollian correlation functions are related to the 4D bulk, I mean, amplitudes by this what, you know, modified embedded translations.
Let me ask you,
Yes,
you know, I was very confused when you said in some formulation, not yours, where we just get the sphere that the weights change under translations, right? Because, I mean, if I thought about, say, word identities and so on for the physical translations, usually one likes to have some notion of a, you know, primary operator, which where you don't change the data for that operator.
yes.
You know, we look at word identities for various symmetries, right?
Yeah.
The transformations of that primary field, let's say, are determined by data corresponding to
That's right,
like
that's
its weight and so on.
Yeah,
But you don't change the primary
Yes,
field, right?
yes.
And then you get word identities.
Yes.
So, I mean, it was a little confusing for me how that would have worked if I was to change the weights and so on. Are you saying here, if you keep your U direction,
Yes.
that you have a notion of primary fields perhaps as the field?
I mean, so yes, that is what I'm saying. That is the thing that I'm saying, that, you know, so what I'm saying is that previously what had happened is that people looked at the you know, the subgroup, the, I mean, SO31 subgroup without looking at the translations. And the CFT that was, I mean, was and went on with the notion that the Lorentz group at I mean, at infinity is going to like work like a global conformal one, and we will define primaries for this and so on. But that, since that didn't, I mean, take the translations into account, it had the weird feature that if you did a translation on these primaries, the weights will shift. What I'm saying is that if you did not do that, but if you also included the translations in your formulation to start off with, thereby you had not only the Lorentz group, but the full Poincare group. In that case, and you were to define primaries not with respect to just the the six zeros and plus minus ones, but you also included the translations in them, then things will transform in a nice way. You will not get shifts, and that is what we have been trying to do.
So just to ask you, so you have the full Carrollian algebra,
Yes.
it includes super translations, in particular also translations and your LLs and all.
Yes.
Now, is there some nice notion of a primary field under this algebra?
Yes, that is what.
And then I organize everything.
Yes, that's the program in some sense. So we you arrange it. So the crucial the crucial extra bit is you also include this in. This is the crucial, yes.
Your super
Yes.
translations.
Yes.
Right?
Yes. That's right.
So you include them, and then what is the meaning of a primary? These rules.
These are the rules. So, So I will have a weight H and H bar of these guys, and I will say that these these are my the highest weights. These are the primary fields basically. And what I'm saying is that these, when you write down the action of this, it is the same as the thing that you had got earlier by just translating stuff.
I'm trying to understand that statement, MRS 50.
Yes.
If I think in terms of a killing vector field,
Yes.
this MRS is some shift of U in a Z dependent.
Yes.
Now, what kind of insertion of phi will be invariant under that? Because the phi is inserted at some U. So I'm not being very stupid, but I couldn't see what.
So this is just if you wish, this is the equivalent of the
I think you're going to say that's the equivalent of conformal killing.
Yeah.
K and
Yes.
But now K is a killing vector field that vanishes at the origin. Is a
Sure. Yes.
So I was trying to understand what the analog of that is here. What this vector field MRS.
Yes.
It is a U-dependent translation. It's a translation in U.
Yes.
In some Z-dependent way.
Yes.
Where does it vanish? You need that it vanishes somewhere, right? Otherwise, how can what is zero? I suppose the other way of asking it is phi of zero. What is zero? What does zero mean?
Zero means U equal to zero.
U equals zero. Why is U?
U. So it's at this point. Well, it's not this point. It's. We will. So you want to start off. So what goes from minus infinity to plus infinity?
So it's somewhere in the middle.
Yeah. So here, say.
So why is that not moved by a generic MRS? Sorry, so there are two questions. Just geometrically.
Yes.
Does MRS move that point?
Does MRS move that point? It's a translation, yes. So it will.
It moves it in some U-dependent way,
Yes,
right?
yes.
Then how is phi of zero annihilated by that? Why don't we get a derivative?
That zero and phi of zero.
No, right. So it's also Z. So it's U. Then Z bar equal to zero, basically.
Fine. So
yes.
What is special? I'm trying to understand what is special about. Is that killing vector field vanishing at U equals Z bar equals zero?
So the killing vector field would be like this, say. So it's a del U, if you wish. So you
it's del U, but weighted by Z to some power. Is it Z to some power or E to the?
So when you have say this object. So let's try and so M zero is going to so M0 is just going to be your time translations basically.
Yeah.
And what we also we want some, so this is just Poincare invariance of something basically translated to the field theory line.
Right, just let me understand. You've got a sphere at infinity and you've got this null direction.
Yes.
All points on the sphere are the rotationally equivalent.
Mm-hmm.
So there's no distinguished point on the sphere. So choosing some point on the sphere, same as choosing any other point on the sphere.
Okay.
Okay, so your vanishing can't come from choosing some special points on the sphere. Then it must be coming from choosing some particular special point on U, but there's translation in there.
But I mean, if I were to just do this thing, and this all, so
Was it inserted at some particular location?
RS actually is Z
Yeah, doesn't it, what is that formula, M N Z to the N plus one D?
yes,
Is it 3 dimensions or what?
yeah, so this was,
But I mean, you have a
this
Z.
was, I wrote this down for the equal to yes, but there will be a similar M
Similar,
and
right?
RS.
But what I'm saying is you're weighting your translation by Z
Yeah.
to some power.
Yes,
Now, aren't you choosing Z equal to 0 in a sense as a distinguishment because phi is at that location?
Sounds great, then I'm trying to understand. I thought, we
It's just that you put it up in the exponent, that confuses me a bit, but okay.
I mean, this is sort of like, yeah, so
I thought Z is just parameterizing points on a sphere.
actually, let's, yeah, sorry. There will be R plus one.
Bar. Yeah, that seems somehow more reasonable. Yeah, but go ahead, sorry.
I mean, so Z equals 0 at some particular point on the sphere, Z equals Z by equals 0, some particular direction, right?
Yeah.
If it vanishes in that direction but not others, isn't that this breaking rotation invariance? I can't understand. I thought physically you've got a sphere around you
Yes,
and you've got a killing vector, you've got the type.
yes,
Now, phi of 0 is something inserted at a particular U at a particular point on the sphere, right?
yeah.
Why is there a distinguished point on this sphere times this, such that this killing vector field annihilates it? Is there some choice of conformal frame or something that makes this do it? That much.
But I mean, if you were to look at just the I mean L's for example, right? In that case, this would, I mean, again, you need to choose choose an origin, right?
You need to choose. See, else, I mean, normal conformal algebra.
Yeah.
True, you need to choose an origin. And once
Yes.
you've done that, killing the special conformal transformation, then that.
Yes.
You can make another choice.
Yes.
Okay, but I thought these MRSs
Yes.
were just U dependent translations in U that depended on where you were on the sphere.
Right.
Now I can choose, because I can choose any function on the sphere, I can choose any point and translate.
Yes.
So how can it leave any point in there?
I mean, he's not including M0.
No, M naught is, I mean, M naught is not included actually.
Only the greater.
M0 is just what? The zero mode on this.
Constant number.
Okay, but still, I can choose. I can get rid of the translation.
No, actually, M00 in this case.
Then you can do anything.
Okay, but if I just exclude the zero mode, I move this much this way, I moving this that way. I can't. I won't find a point that is left in there. Sorry, I'm sorry. I'm just trying to understand. What is the meaning, physical meaning of that?
I mean, so this is the
Is part of the physical meaning that there is a point on the sphere times another ray that is left invariant by.
So you want to, yeah, so you want to think of this in terms of so what in a sense is.
We can talk at lunch.
Yeah. Yeah, all right. Let's speak about this. But yeah, okay. So yeah, what I was trying to stress is that if you I mean put this extra condition in, things transform well under translations, and you can define this modified Mellon transformations in this way. And you know the one of the confidence is that now we have bulk amplitudes which are related to 3D Carrollian coordinates. All right, since we are very close to lunch, yeah. So this is sort of like a summary of what we have. So we have putative codimension 1 and holographic dual. The null direction plays a crucial role. Now we have field that transforms nicely with respect to the whole of the group and not only a subgroup of symmetries. And in particular, translations do not change the weight of the operators. And in transformation, this is something I've not showed you. gives finite bulk amplitudes. So that's that, and so there's there's a lot more you can check what the 2-point functions are, and you can do this from the point of view of the field theory. And then what you find is that if you look at this, and then you find that there is an R branch that is U independent, which we found earlier. That's not the one that we are interested in. There is a branch which has a delta function like feature, and this is sort of indicative of the fact that you're going to be sort of ultra local. On the boundary, light cones are closed up, so you can only have something in U, and it has to be Z1. So you can find this branch, and now what you can do is you can go back to the bulk, and you can look at a 2-point function. Of course, the scattering amplitude is trivial, and you parameterize that, and you find that you're going to get the same sort of delta function out when you do this modified Witten transformations. What is happening is that if there is no, if there's no scattering happening in the bulk, so if you leave it from a point that's chi minus, it goes to the same point as chi plus. So that is why you have this particular delta function setting. So we have a way to cross check that with.
So you have an S matrix.
Yes.
Now, just say a little more detail. How do you go from the S matrix to your structure?
Yeah. So let's.
So you parameterize them. You take the momentum. You replace that by direction times. Yeah, please go. Times what?
So you start off with So what we are going to be doing here. So we want to sort of do a modified Witten transformation of. So you take the S matrix. In this case, we just parameterize it with our storm.
In general, the S matrix depends on momentum.
Yes.
The direction of the momentum, I presume, goes into the Z's.
Yeah, and what we will be doing is that we will see that if you do this, just to get back to the parameterization which I flashed earlier, so that just means that this particular overlap has a form.
No, sorry, just in more generality.
Yeah.
If you have, let's say, a 4-point function.
Yes.
For particular S matrix, it's parameterized with P1, P2, P3, P4.
Yes.
The P1, P2, P3, P4, P1, the direction of P goes to Z1 and Z1. Direction of P2 goes to Z2 and Z2.
Yeah.
I'm trying to understand what happens to the magnitude of P1, magnitude of P2.
No, so these are all here. So what we do is, Yes.
Omega.
Yeah, let me just show you this.
So it's omega, and then you Fourier transform that, and then whatever that Fourier mode is, you call U. Nice.
So we write so since P square is equal to 0, so we write it in a form like this, and so that's the parameterization that you use, and
And then U is the Fourier transform of omega.
So so what we will do is we will do a Witten transformation with these extra U's inserted out here, and sorry, not here. Sorry. Excuse me. Let me just get
That's some modified.
Yeah. So that's
Witten.
no, that's purely his. Not so. Except so the usual. Witten transformation just had this. Now we have an extra I omega u. This epsilon sitting here just indicates that it's ingoing or outgoing. And that's the.
And why should that be associated with the position U? Why is this definition appropriate for?
Right. So the point is that so if you look at how super translations and all act on these particular coordinates, it will transform U in a certain way. So at the moment, just going back, back again. So you would be able to find that, if you use these, these sort of coordinates which are on stride bus, they give you the same answers. So, if it walks like a duck, if it quacks like a duck.
But I should just, I know what my free fields equations are.
Yes.
If I want to know what inserting one of these free field operators is at some position.
Yeah.
I should be able to just work it out, right?
Yeah, sure. So that's so we are saying here is that this is a transformation. This is an integral transformation that is going to take you from momentum space directly to u z and z.
What I'm trying to understand is normally that kind of thing gives rise to Fourier transform. Where did all this value?
So this was if this particular delta had been equal to 1, then this would have been a kind of neutral Fourier transformation.
Yeah. So if I wanted to find the operator at this point,
yes.
Maybe because of use of equations of motion. I see. Maybe that's the point. But if I wanted to find the operator at this point, and I know it in momentum space, I normally do a Fourier transform to localize it at that point. My question, I'm sorry, it's a very stupid question. Why did you have to? It's a kinematical question, right? If you want to localize this operator here, why did
Sure. So what we are trying to do is we are trying to use what was happening here, right? So we are trying.
What Andy and friends did.
Yes.
Okay, this I understand. But I thought you had an independent notion of inserting your operator at a point in space time. Is that?
That's so what I'm trying to do here is from the point of view that this was something that was done earlier in terms of
you can use mathematical transform.
Yeah, all I'm saying that look, let's sort of translate these. Make these into operators where U is also there. So we have just
you translate U in some mathematical way. Now I want to check that is the same notion as the physical point U on your.
Yeah, this is something that I'm not saying here, but yes, that's something that can also be done.
So this is what I'm trying to understand how you can do that. So if you did that, I would have imagined you would get some sort of Fourier transform. I feel there's an equation of motion that I'm not using in what I'm saying. And that's probably what will give you a, but I just want to hear.
So you could look at bulk points and you could sort of take them to the boundary, right? So that's something that you can do. And you can find the sort of extrapolate dictionary.
Just one last.
Yeah, sure.
But if I have an energy along this direction, I want to localize something at some point.
Yeah.
I'm Fourier transform.
Okay. Yes.
Why are you doing more than?
What do you think? What is this factor of omega?
That's something like.
That's just the. So we are changing. So the basis is being changed into something else basically. That's all.
But it changes whether you localize it.
Yes. Could you interpret it as some frequency dependent renormalization? Meaning holography happens. You have to renormalize it.
Maybe.
I'm not seeing it.
But in the end, aren't you dealing with a wave packet that is not localized anymore? So why is that?
Are we dealing with a wave packet that is also localized?
Your question, if you take your left-hand side, would it be localized near particularly U? Yeah, this is, suppose I construct a bulk wave packet, I take creation operators, A daggers, take some bulk wave packet, subject it through your transformation. Would it end up being something local? This is your
So that I can associate it with the physical space standpoint.
That would be like a naive extrapolate. Like take a bulk of
Yes.
We know that has issues.
Okay.
So I suspect that this is some way of curing those.
Yeah, my point of view, as I was saying, is that there is this map between the 4D and the 2D case, and all I'm trying to do is I'm trying to include in that map way to make sure that these transform nicely under translations as well. If I do that, this is the thing. I mean, I get. But I mean, so I do get. I mean, what you're saying. And there is an, I mean, extrapolated way of trying to
Shiraz would be happy if you say, yes, it's not quite localized, but it transforms nicely under your Arjun. Something. I don't know.
I'm not sure if I can make that statement, whether it's localized or not, but yeah, I mean, so the
But it does transform nicely under.
yes.
I mean, what is even the meaning of local? Like in standard quantum field theory, we say local operators have causality properties, right? They commute with their probability operators.
Yes.
What is the analog of
So
that?
this would be null like localization basically. So where you try to make sure whatever you are doing in the usual tide-like ways is sort of extrapolated when you have a null direction.
But I would say that if you make a difference between beings very large, then
Yes.
the correlation from them to. Why would that be? Yeah, and I mean, localized in that sense.
See, the point, so the rules of the game will have to be sort of redone basically, because light cones on the boundary theory have all, gone. Yeah.
I see.
So these are-
Shiraz should say, and I have to run, I'm sorry. But I thought here, at least I understood, because I thought localizing means lump is lump. I have some classical way of going at the speed of light along some direction. I keep the direction fixed. The lump moves, T
Yeah,
is linear.
sure.
So his point was, if it's localized in the bulk, after you send it through your transform, will it still be localized in that sense, right?
Yeah.
That's how I understood. So, sorry.
Yeah, let me just wrap up and say something at the end.
Just to say that this may also be the answer to my other question. If you're not taking something localized, then it's not acting by just geometrically killing the effect of how it acts on a point. And then let me explain it. If you're doing something else, then all my intuition.
So let me sort of summarize, I guess. This has been not what I planned for, but yeah. So
That's
what
part of the strategy.
yeah, that's a part. That's a part of the fun of being here, of course. Things are not what you planned for, of course. So what we saw is that this Carrollian physics emerges in the vanishing speed of light limit of Lorentz in physics. It's sort of natural as a holographic duals of flat spacetimes, and we have done some work in the 2D case, and so sorry, and yeah, so let me so at the end we also saw a way to reconcile what scattering is, and try to address this in under three-dimensional field theory. Things transform in a nice way, and there have been so there is a lot of ongoing work as well, which we are trying to figure out a lot of corners of this, and I think let me sort of wrap up and say that let's so I'll wrap up here, but I'm happy to chat for the rest of the day, and it will be.
I guess there were a lot of questions, very interesting questions.
One last.
Yeah, sure.
Maybe this is what Shamik also told us.
Yeah.
But in a paper Omkar and I wrote, others wrote some time ago, we had a relationship between the bulk correlators and the S matrix in the following sense. Then you choose the part of S matrix and bulk correlators in the following sense. Then you choose the part of the S matrix, it's a bulk correlator that has the pole. Okay, and the coefficient of that is like the S matrix. Okay, and so then you could invert for the bulk, that part of the bulk correlator that gives rise to the S matrix in terms of the S matrix. Okay, in terms of boundary S matrix. And that inversion has this extra 1 by p squared.
Okay.
Which was not just a Fourier. Because of that 1 by p square. Is that the same as this millimeter? Because between the S matrix and the correlator, there's also a
Okay.
perhaps that is the same as this extra factor of p. Delta, yeah, but then this delta goes away in the end, right? Yeah, because in the end, your things are not parameterized by delta.
No, it is.
Parameterized by delta. I thought delta was.
No, there is an, HH bar for, all of these guys here.
Delta was what again?
Delta is H plus H bar.
No, in terms of the bulk fields. It's a mass.
Delta in terms of the bulk fields. Delta in terms of the, so this is the weight of the L naught and L naught bar. So these are going to be related to so that will be the mass and the spin. So
That sounds.
Yeah.
Sorry, I thought it was mass.
If it's if you've got a
No.
massless scalar field, then it's a particular value.
yes.
And delta becomes.
Does delta become what does delta
So
become?
and delta would be delta is so if you have a massless field in that case, so this is for example, if you so that will be so H plus H bar would be the sorry. Let me just, why am I blanking out on this? Sorry. Yeah. So, for example, if you had a massless Carroll scalar field, then it will have H and H bar equal to 1/4, and that that particular object, it's the L naught. So the L naught is the super rotations, right? So that's not, it's not the mass in that case. So the fact that it is massless, so we are doing massless things out here basically. So
there is a particular value for delta.
yes.
A fixed value.
If your fields, you give me the fields that you want to, throw in, and we'll be able to fix that for you.
Massless minimally coupled scalar.
Yeah.
In bulk.
Massless minimally coupled scalar and the bulk will lead to some particular.
Yes,
right?
yes.
Okay, that's